Hi, everybody. Welcome to the Pavilion panel. Today we're going to discuss a topic that's emerging as something that we got to care about so we don't hurt anybody. You know, steering safety innovation, autonomous cars through their electronics. We have folks that actually practice this, so we'll try to understand their concerns and their challenges. So the way it's going to go today, I'll read a few slides. Introduce the panel. The panel is going to have a position statement. Each guy is going to talk for about 5 minutes. And then once we do that, I'll have a couple questions. And if time permits, we got about 45 minutes. I'd love to have questions from you all, if that works for you. So basically, look, the sophistication of electronics in cars is getting a lot more complex. The problem, of course, is that cars aren't cell phones, right? You just can't let it turn off. It actually is on a mission-critical mission, using the word to define itself, anyway. But with that said, though, how do you ensure that your software and hardware are working properly in the car to ensure no one gets hurt? And so the other challenge, of course, is that we're asking for space level or aircraft level quality in cars that cost, a lot less than an airplane, for example. A 777 stripped down from Boeing is about $250 million. A Ford Concourse is about $22K. They have about the same level of ICs and complexity, yet they got to sell for a lot less. So one of the challenges each one of these guys is going to talk about today is bringing that capability to market at a reasonable price. So we'll hear some about that. So I'm Jim Hogan. I'm a venture capitalist. Been in the business a long time. I've had a bunch of EDA-ish assignments over the year. Probably the one that most people know me for is I was at Cadence and I was CTO of Cadence. I've been a venture capitalist for about 15 years, running my own fund out of Los Gatos. I do some EDA, some semiconductor deals, and as a result, they have me do these panel discussions. You be the judge whether they're making a mistake or not. Nandan is sitting right with the lovely blue shirt on, right? He's got a really important job at ARM. He's ensuring that they're head the right way for the CPU division. ARM is so ubiquitous in the ecosystem that it's going to be really interesting to hear how they're going about this and what their concerns are on automotive. As you can see, he's a very well qualified candidate with a lot of experience. Looking forward to your views, sir.
Thank you, Jim.
This young man right here, Martin,
Hey,
he's
I'm young too.
My apologies. Everybody's young compared to me. Okay, so it's a relative statement. Okay, Martin's next. Martin, I think he missed the phone call that day, and he was the guy that got selected. And so I'm really happy you're here, right? But he's working at Bosch. Bosch is a dominant supplier in the automotive ecosystem, as most of you know. He's also had a load of experience elsewhere that makes him very well qualified for helping us out today. Thank you for coming. Right is the tall, slender, handsome fellow there, right? He's the CEO of a company called OneSpin, which is a formal verification company. Formal verification, I think, is, at least I would say, is becoming the third leg in the stool of verification along with simulation and emulation. So I want to understand from him what formal guys are doing in terms of ensuring quality in systems. The last guy, to my far less, is Philippe. Philippe, I've known for years, right? He's an interesting guy. He's had a job at Bell Labs when Bell Labs actually existed. Bell Labs, for you young guys, might not realize it was a premier R&D facility for all of electronics, not just communication things. For God's sakes, a transistor was invented by Bell Labs. And so it's great to have Philippe here. And a little known fact, Philippe was actually born in Britain. There you go.
Is that
right?
good or bad?
So anyway, I'm looking forward to hearing what's going on in ST. They're a large supplier to the automotive ecosystem. And we'll get this started. Martin, how about we start with you?
Yeah, of course.
Can you talk to me a little bit about what you think about this?
Yeah, so the point is, like, I'm here the guy who's not with the semiconductor background. I'm here the supplier guy, like Bosch. What are we doing? We listen to the OEMs. They have special requirements. They want a new device. Then we have to go to the semiconductor guys, get the right chips, assemble them on a board, and try to make the OEMs happy. And actually, that's a hard job because we as well have to ensure safety. And I think everyone here heard of ISO 26262. That's a standard established in, what was it, 2011, right? So before 2011, I was working at Audi. We didn't have this ISO. Afterwards, I called some of my friends there. I asked them, okay, what changed for you? And they said, basically nothing. We just followed this ISO. We had the same thing established. But the problem with this ISO standard is, for us, that basically we see that it covers a lot of things from the semiconductor industry. So we see that it helps people to develop devices, so small devices, chips, and so on, and only one device. But we, as a supplier, we have the problem that we build larger systems from these devices. And we also, that's even maybe a bigger problem, we have to make all the OEMs happy with all the different requirements. So we have a lot of variants that we need to supply them. And that means we have all these different combinations of these chips on the boards and the software and so on. And for that, ISO 26262 doesn't help that much. And when you look at it, this panel is also about autonomous cars, right? And we talk about semiconductors for autonomous cars, and there are autonomous cars, there are semiconductors. There are so many layers in between where so much can go wrong, yes? And that's a real big problem that still needs to be addressed. You have things in the future like we will have Linux in the car. More and more we will have apps in the car where you have all combinations of different software. And then we have over-the-air updates, things like that. And that's not covered by the ISO. So we need to find new solutions for that, also together with the semiconductor guys. So that's basically a short statement from my side.
Yeah, so basically you're saying the ISO standard sucks, and we need to come
No, it's helpful for them. It doesn't help us that much. You know, they can just say we covered our bag with the ISO standard and everything is safe from our side and everything, the rest is your problem.
Yeah, I apologize for that. Was a very Cooley-like comment, and so I'll move forward. Thank you. Nandan, would you please comment, sir?
Sure. So a couple of things I might slightly disagree with you. ARM, as you know, is known as providing processing solutions for smartphones and other embedded equipment. And of course, we refer to these as, at the high end of the smartphone, as a premium mobile device. Recently, a luxury car executive said, with the amount of electronics in my top-of-the-line cars, I think that's the premium mobile device, and I can charge 100 times as much. And you can't disagree with that, right? And ARM's kind of road into the automobile rather than just a mobile has come through kind of what used to be very deeply embedded solutions that went into ABS, then went into window controllers and the like, slowly moving, of course, as the platforms got better into IVI, ADAS, and of course we're looking firmly at the possibilities of doing or supporting the industry as it goes to autonomous vehicles. And ARM's product line effectively has multiple products that are tuned for various things. So things that need critical response time, very predictable response times, obviously safety considerations, and then of course high-level, very scalable compute. Now the point of disagreement, I was going to say, it's not that your car is not off, you just don't want it to reboot while you're driving. Yeah. Right? And to that effect, I think it starts from the hardware, as Martin points out. As an IP vendor, I do look at a software or a safety element out of context. We use the ISO standards to ensure that according to those rules are fine, but when you put it all together and layer on top of it, there is a bigger problem that needs to be solved, and we understand it. And it's not going to be defined by a standard, just by a standard primarily because you are going to have ambiguity in those standards so that they're not completely constrained. And when you have ambiguity, there is room for engagement. So ARM has focused on at least getting the standards right, so we know what we're designing right, by investing over the last nearly a decade into design practices that that capture requirements, track requirements, and effectively it's part of our entire design process for every product we build on the processing side and the other IP as well, more and more so. And we've been also building our capabilities to support recovery from random faults as well as systematic faults, right? And this is not just a CPU solution, as you know. It's not even an SoC solution. It is how do you actually support the software stack on top of it? Obviously, we can look at our part, but we need to kind of work with Philippe's team on actually delivering SoCs, use guys on the validation, and of course the tier ones and the OEMs to actually make sure that that works.
Thank you. Now let's hear from his crosstown neighbor in Munich, right? Would you let us know what you're working on, please?
Yeah, so what we see, as Martin said, that traditional automotive suppliers like Bosch, they have processes and things in place that actually go beyond the needs of ISO 26262 in terms of functional safety. And what the standard does, though, is it allows other companies to go into that market that haven't been involved into that business before. So it gives them a guideline on what is needed in order to achieve a certain amount of functional safety. And has been remarked before by Nandan, it's two aspects of functional safety that we look at right now. That's the systematic faults or systematic errors that you need to eliminate. And on the other hand, it's the random errors that are basically things that happen in the field to your device and break the functionality. And on the former part, on the functional verification side, the systematic errors are something that we can target with standard techniques that EDA has been providing to the industry for a long time. So it's basically making a systematic approach to verification and having a coverage to prove what type of functional verification you have done. That is basically the same thing that we have been doing before. So there's just more systematic in it and more traceability. That's what you add to that flow. On the random errors, it's a different story though. And there I would think that also the standard makes a bit of an extension to what other automotive or traditional automotive suppliers have been doing so far in terms of how much you have to care for these random faults and how do you deal with them. And that's where OneSpin is working actively right now to extend the capabilities of formal solutions in order to target these questions of how do you verify a safety function, how do you prove that you have a certain level of diagnostic coverage in your chip. So that's really challenging. So that's a challenge for the EAD industry in general. You can think of the fault simulators as well. They're struggling getting all these faults simulated that you need to do in order to get your coverage data proven. So it's not just that you have to run it, you have to also prove that you have done it. And that means you have to collect all the data, you have to store it, and you have to present that to the authorities in order to get your certification, right? And Formal is a good tool that helps to actually achieve that easier and faster. And that's what we are working on right now.
I'm waving to Oz as you're talking about Formal, and I suspect he wants to comment. There you go. So, Philippe, actually, this is like we designed a pretty good panel. We have the hardware guy, right? The guy that's working on the system. We have the IP guy. We got the EDA guy. Now we have the guy, Philippe, who has to build the semiconductor. What kind of challenges you seeing on this?
I was going to say, so all of the responsibilities on our shoulders at the end, in the sense that we have to provide the hardware that actually executes on all these expectations. And I like to say 26262 is say what you do what you say. So specification that you have to check and that you implement it correctly all the way to the hardware and then all the way back to the software and the system. So ST has been in the automotive business for as far as I can remember, which is, I would say, 20 years at least. And we are one of the top, few vendors that are successful in this space. And clearly, there's a very, very high barrier to entry in semiconductor for automotive because of the high quality standards that are absolutely required. For obvious reasons, you don't want that when you put your foot on the brake, nothing happens. That's not such a good thing. Or when you turn the steering wheel that is now steering by wire, you want the car to actually turn the way you intend. This is all obvious. So we have been starting initially with smart power, what we call smart power, which is very sturdy, high voltage transistors, high ampere transistors, and actually we've been partnering with Bosch over the years on that, co-developing this technology. And partnering is actually the name of the game. If I wanted to nail down one single parameter that makes this successful, we are such a complex supply chain, value chain, I should say, value chain is better, that partnerships in order to address the complete solution is the answer. But having said that, over time we have increased the breadth of our solutions to digital, and especially now we have a very solid microcontroller solution that is today in production in 90 nanometer with embedded flash, moving to 40 nanometer with embedded flash. Today we do not use ARM cores for those yet. We have announced that we have a partnership with ARM, another partnership, in order that the next generation would be, which will be most probably 28 nano, will be based on ARM. And moving on to 28 nano, this opens up both a breadth of possibilities because so much digital function can be put on the chip, as well as obviously responsibilities because we want those functions to be working. And it so happens that in another branch of ST, at the same time that this was happening on the automotive side, the telecom, or let's say cell phone branch, we were developing this technology called fully depleted silicon on insulator, FD-SOI, for specifically the reason that it's perfectly fit for cell phones in terms of very low power, high battery, high performance, very flexible. For different reasons, we exited that market, so we were left with this baby, and we kind of found out as a side effect that the same technology is actually an extremely good fit for automotive because of the SOI layer being so efficient for radiation hardness and actually soft error rates resistance. And let me just give an example that is more pertinent to the discussion of today. We think we can reach an ASIL B type of hardness, which is typically an application that is not life-threatening. Life-threatening is ASIL D, as in whatever dog, and ASIL B as in boy is what we're talking about. We can get rid of the normal solution for processors, which is lockstep, which is you have to have two processors that work with each other a few cycles apart, and they keep checking each other. And if something happens, it means you have a soft error, you stop the system, and you restart. So which is very, very power hungry, very inefficient in area and performance. And we can get rid of the lockstep by having this sturdy technology called FD-SOI. I will not go into detail, we have papers on that. But sufficient to say that we believe that we can, with that technology and a combination of design methodology, fault injection, and the like, to determine which are the flip-flops that has to be hardened. Let me skip the details. Essentially do a processor of the size of an A53 to give some order of magnitude. So 64-bit quad-core from ARM with ASIL B sturdiness without going to lockstep. So you can imagine, power consumption divided by 3, area divided by 2. Less power means that you can obviously fit more function in your dashboard for the same silicon, or more function. Same function with less silicon, less power, or more function with the same silicon. So we think that not only we are here, and we are very strong in that market today, but we are on a path where we clearly will continue to lead thanks to that solution that we are putting in place. And this is not just talk. We have 3 products that we have announced publicly, one of which will be sampling this year, for satellite radio with the Sirius XM, which is another partner that we have. We're working with Autotalks in terms of vehicle to vehicle, also on 28 nanometer of the SOI, and we're working with Mobileye, and we will have a product next year that will be level 2, level 3 resistance, or let's say autonomous driving levels with Mobileye by next year on that technology. So this is not just talk, this is real. We have products sampling this year and production next year.
Thanks, gents. Thanks for your position. Now for a question, right? Hey, so if you look at new car ownership, I'll make it United States statistics. It's probably true for the rest of the world, but let's say U.S. You buy a new car in the U.S., you keep it for 10 years, okay? That car has a resale, and it lives for another 10 years. So look, in my experience, and I think this is true if we use the analogy of airplanes, things prop up over that useful life of 20 years that you can't possibly anticipate, in my opinion. So tell me how you're going to keep the used car guy safe 20 years from now. All right? So who should I pick on first? Let's ask the gentleman from ARM first.
So the beauty of it is it's all programmable. It's a software patch. No, so if you look at how do you keep something that's in the market 20 years current, if you will, I think the problem will start with, if you're talking about, it's not one product that is going to be the issue, right? What sensors you need for a different type of protection, I don't think you can replace that. So there will be an aftermarket set of solutions that, I mean, that exists today, and you could argue has more relaxed safety requirements. I expect more, as we get to more aftermarket, there will be more constraints on how those products are pass certification as well. Currently, most of the burden arguably is still taken by the OEM and then the tier one and the silicon vendor and after. But when you go to aftermarket, I think there's a different, what should I say, economic or liability challenge that needs to be sorted out. So in reality, I think the future of that still needs to sort out as to how we do that.
Yeah, you know, I can hardly wait to go out to my garage and start my car, and it's like Microsoft, right? So I'm getting 19 patches. You know, that takes about 25 minutes before I can even turn my car over. I'm looking forward to that.
Well,
Okay,
Tesla
Martin.
is on their dates today.
Yeah, there you go. There you go. You know, I mean, you know, everybody's got a cell phone here. Everybody's got a smartphone, and we're constantly getting updates. At least Apple sneaks them in a little better, right? So, Martin, what are we going to do about the long-term potential reliability issue and reliability and safety issue?
I mean, for us, as a supplier, if it's a problem with the chips, it's easy. We can blame it on Philippe. And I understood Philippe anyway. What you said, you have everything under control. So that's the same thing. I mean, really, what happens in
we'll catch it with the patch.
Yeah.
Well, you know. Yeah.
What happens in 10 years is one thing, but we also have to look at the current situation. What I saw is since 2011, since ISO 26262 is in place, the number of recalls because of software failures tripled. So that's already the problem that we have nowadays. If then some hardware problems will add up on this, it's really going to be a mess. And I think.
So what are you saying? Don't buy Audis?
No. I say you have to accept that the car industry is more conservative than other industries. So that's why cars don't have the latest stuff in there. You can't compare a car with an iPhone. On the other hand, people want to have the latest stuff there. So that's maybe something that has to come up. But the other thing is what the OEMs want now is to reduce the number of devices in the car. That's like their biggest goal already for the last 10, 15 years. And then maybe that's the chance, what Nandan said, that we will have the opportunity just to reconfigure it. Some device fails, okay, we just have some degradation, some functions won't work anymore, but they will work on a different device.
No,
but that's something in the future.
No, but to add to your point, let me start with a reference that Jim made earlier. He talked about the a 777 Boeing being 250 million and a car being 22,000. If you actually take its kind of younger brother, it's 787, which is a totally fly-by-wire plane, can you imagine the number of lines of code that were developed for the Dreamliner? Any guesses?
Oh, I'm going to say
About
50 million
93,000.
or something. Yeah.
93,000.
Yeah, wow.
Do you know how many lines of code are in your mid-range Mercedes car? Forget Audi. Sorry.
Let's talk about the guys in Stuttgart.
Well over 100 million, right? So
100 million.
I think you are going to have this software problem not in the future, already today. And for that, I think you need a couple of technologies at least in your system. One is things like virtualization, right? So where you can actually partition off processes that don't work and recover smartly. So when you're talking about, and this is not your standard virtualization, it's still need to be real time. So it's more hard real-time virtualization, which is again a challenge, which ARM in fact is announced in its next generation architecture for automotive. And then of course you had to have a better mechanism on testing the software along with it. You are not going to change your automotive software, at least on the safety critical parts, anywhere near as fast as you do on the what do you say, standard?
Your printer driver?
Yes.
Hey, right, you know, you're supposed to be able to cover every state with your tool, right? Every
absolutely.
state. That's
We do
this,
everything.
that's the value prop, right? So how are you going to keep us from getting killed?
Yeah, I want to actually add to the problem, not to the solution first. If you believe that Philippe's chips are just the best and everyone's buying them, right? Bosch's putting them into their devices, and there's going to be a Bosch device in any car. So if this chip fails in the hardware, you're looking at a scenario that I call the total recall. So every car in the market is going to be affected. That's a disaster, right? Mm-hmm. It's a commercial disaster for the car industry. And the risk drivers are not just the aging that you mentioned, Jim, it's also the integration density. So if you look at 28 nanometers or below, structures get so small that the energy you need to incur an event is going down. If you reduce the voltage, you need, again, less energy. And if you have more functions in it, more stuff on the chip because it's just bigger, again, there's more that can break. So you have 4 vectors going the same way, and that's adding to the risk. So there's no way around upfront design to actually prevent that scenario. So it's really important to understand exactly what your risks are and how to mitigate them and how to make sure these things work.
Well, you know, I love you, brother, but you're telling me no hope.
There's another thing that another solution that I want to add to you.
Okay.
Get rid of your cars, Jim. You're going to have a self-driving car, but it's not going to be parked in your garage. It's going to come to you if you need it, and it's going to go somewhere else in San Francisco in the meantime, enjoying itself.
That's the great fear of the automotive manufacturers. No one buys a car anymore, right?
That's the other scenario. You won't use them. The self-driving cars won't be out there for 20 years. You will.
Well, you know
6
what?
years and they're gone, like your cell phone. 3 years.
You know, that's a problem you guys got to deal with. I'm not going to be around by then. So, I mean, you know, good luck with it, you know. So, Philippe, I thought you said something that that was really interesting, right? That, you know, a lot of these current systems have lots of redundancy, right? So one of the keys to saving power and increasing density is come up with techniques that assure reliability and safety, but don't have the redundancy. Can you talk a little bit about that?
Yeah. First of all, I want to say that I see a use for cars, even though there's utilitarian view for cars, which is that you need to get to work, and that's a pain. And therefore, that's a use case where the car can come to you, it brings you there, it brings you back. Then there's another use for cars, which is to have a fun drive in the mountain and to have fast speeds and things like that. I'm still a fan of having manual drive for that, not autonomous drive. Mm-hmm. There's pleasure in that. I was happy to see that the vehicle-to-vehicle Wi-Fi standard can work up to 500 kilometers per hour, such that if you have 2 cars that run against each other at 250 kilometers per hour, they can still communicate with Wi-Fi. So that's a nice use case. I like that. Having said that, the thing about the redundancy. So what we do is actually we have a homemade, homegrown version of fault simulation where we inject faults that are simulating radiation, soft errors randomly. And based on that, we run a lot of statistics and what if scenarios where we say, okay, let's make this flip-flop redundant, but just this flip-flop, and see whether we come up with a solution where this, the other errors, eventually wear out and they don't affect the actual system decisions that are critical. There are obviously, state machines are where you want to have, flip-flops that are really, really solid. Data sometimes, especially if this is a camera that is looking at bits, some of the bits are wrong, no big deal. And so with those methodologies and the fact that the FDSOI is actually more sturdy versus soft errors, combination of the two, we think that we essentially, with an overhead of about 10% of area, we can actually come up with a ASIL class, which is ASIL B. So that's a pretty good compromise that we have come up with. Obviously, we, in the case of processors, we have some more deterministic analysis that is looking at instructions that are critical, areas of the code that are not mission critical. So, for instance, if branch prediction doesn't work, it doesn't work, but it is not mission critical. If, on the other hand, the program counter is corrupted, that's not a good thing, right? So anyway, so we are applying all these techniques, and we're learning as we go, and we're getting smarter, and I'm partnering with these guys, the processor guys here, obviously on that, and with these guys, the EDA tools, which we think obviously more cycles and more efficient fault simulation is another angle that we need to take. So these are some of the ideas.
Yeah, I mean, it's going to save a lot of 10% premiums, nothing when you get rid of a whole processor, for example. Right. And it probably has a lot of opportunity to save energy as well, I would guess. That might be my guess.
Thank you.
Yeah.
So Martin, you just heard this, you heard what your supplier is going to do for you, right? What do you think about redundancy?
Yeah, to be honest, I think that these guys are doing an awesome job. Like I feel from my position that the hardware guys more or less really know what they are doing. Like they have everything under control. Okay, when it comes down 10, 20 years down the road, what we talked about, we trust you. Let's put it like that. That's the only thing we can do. Like we don't test these things, okay? We just assume that you tell us it's gonna work in 10, 20 years, and we trust you. What we need more is like to work together with the ARM guys who want to provide the middleware. Until now, what we have as a supplier with the OEMs together is this AUTOSAR standard. And like personally, I never met anyone in the automotive industry who said, that's awesome, that's helping us. Everyone said, okay, it grew too big and it's now a little bit a problem, and we need something that is safe and agile at the same time. Because now it just stops us from being productive. And therefore, my hope would be like that we as a supplier get closer to work with ARM. I met here some ARM guys who are doing embed and so on. Like in the automotive industry, not many people know about these things going on. It's still software-wise, it's a really old standard we are following.
Right, I mean, to take up on Philippe's point, as you get into more autonomous driving, right, it's not just a quad-core A53 class product, as you mentioned. These are going to have much, much more compute and potentially, with vision, et cetera, even larger amounts of compute. So expecting full redundancy on that is just going to be impossible, just from a cost perspective for silicon, but also from a thermal perspective. And by the way, there's a separate side to that. Most of these things are not just power in terms of thermals here, but you need them to be actually able to wake up and work when you're in the middle of Death Valley on a very hot day, right? So power is important in various ways. But coming back to the point, you are going to need more probabilistic scenarios as well. Certainly having process technology help you with the redundancy is good, but you're still probably going to need additional, as you say, if it's a cost of 10% area, but you have more predictable a mission critical piece aligned with the not so critical piece. And that, again, needs a software layer or a standard that is more agile.
Yeah.
And we are certainly working, and I don't think it's
Yes,
the same
so-
standard
so
everywhere.
I would add that certainly, the software, we're only seeing the tip of the iceberg at this point, and as you said, millions of lines, hundreds of millions of lines of code, and of course, there's classes of software. Obviously, virtualization is one angle to the solution because you have these compartments of,
Right.
critical software that is isolated versus non-critical software, and that's a must, and
Yep.
we are working together on such architectures. But we need to come up with innovation that is not even thought of today, such that software can eventually have the same level of reliability than hardware has today. As you pointed out, hardware, we've been working at the problem for 50 years, so we are pretty good at it. And we can still improve, and especially we are pretty good because of redundancy. We can be more efficient, having less redundancy. And we will be cautious and doing it gradually. But software is certainly the place where innovation is welcome. So anyone out there wanting to do a startup, that's a good place to start.
And the only thing I'll add to that is this is not just a standard that goes everywhere, right? So effectively, what I need for my window controller is not the same that I need for my vision system. So these are not kind of a blanket set of standards. These need to be more tuned to the applications they have. And once you start at least having a common thread of the S word that we haven't used, which is security, that again is an important piece because
so we
any
talk about
points of
safety
attack-
very much, but security is a good thing. You don't want the famous hacker coming into your car and
through the smallest point of attack.
through whatever, the weakest
No,
link.
the breach always occurs at the edge, right?
Yep.
And so the OnStar system will run your Oldsmobile into the wall, right?
Correct.
So,
And
Hey,
from
sir-
our standpoint, at least the standard we think we are working on with the entire industry on that is trust zone,
well,
which goes all the way down to the little guy now.
Well, so I'm gonna throw it to Wright first, right? So Martin tells me the ISO standard sucks, right? Nandan says, hang on. I'm the question asker,
it's
but
perfect for Philippe. It's not good for us.
okay, it sucks, but with a caveat.
Yeah.
Okay. Nandan says, hey, you know what? ISO says that you do what you say you're going to do, right? That's what ISO says. It doesn't tell you how. It kind of tells you what. Okay, right. How are we going to do it?
So it's a good question because that's something that we explore together with our customers right now. Everyone is learning on how to implement the ISO 26262 requirements. So it's not that you can look at the standard and say, I'm going to do this and this and this, and I'm going to be safe. What we've seen is there's one critical property that you want to have, and I have to go back to what Philippe said. This is branch prediction. I wouldn't believe that. Because what you need to show on different levels in your designs is the isolation property. That means that faults cannot propagate from one place to the other. I want your proof, and please use formal for that, that the branch prediction failure would not affect any critical function. The same way you would do that in software with your isolating the virtual machines from each other or running things. You would need to have a certain amount of verification on that actually this is what you do, or your controller example for your window controller. Is it really sure you're not affecting any other function when this thing breaks? So, and I think that's an interesting thing because isolation is one of the key properties for security as well. So you see a very much overlap between safety and security in terms of the methodologies that you apply. Another one example would be in that sense, you can't design, you can't get security into a system that's already there. Same holds for safety. So you have to design safety into your system, you have to design security in from an architectural point of view. And the way it's done, and that's again the same pattern. You start implementing that bottom up, and you prove your isolation properties in a sense, and then you go one level up and have a failover that catches exceptions from that rule, and then you go above and above, and that's the same thing repeating the same pattern. If you look at chips, you have maybe TMR flops, so you have a bunch of flops safe. Okay, great. What happens if 3 or 4 fail at the same time? Okay, you take another signal from those flops to an error management unit to collect how many of them are failing. You pass that signal on to your software layer, and that's taking care about the healthiness of the chip. It's rebooting it if it finds, okay, this function is failing, and so on and so forth. So that's the same pattern that you apply, the defensive strategy. And I see that in both safety and security. I think there's a lot of overlap in how things are done. And I think that's what we should maybe get into the standard too.
As some of you may know, I wrote this article on formal verification, and I had this notion of synthetic vectors, and he says I was full of it. So I'm going to resist the temptation to beat him up right now. Okay. Okay. So let's look at this picture for a second. We got this lovely family riding down the highway playing checkers in their car, right? So quick comment, I lease a car every 3 years, and I got a 2016 Mercedes that does a lot of stuff, but my IT guy bought a new Tesla, a Tesla 85D. Now, I live over on the coast and drive over to Los Gatos all the time, which is a treacherous mountain road. And so one day we put his Tesla in drive mode. So we had the Tesla drive the 25 miles from Santa Cruz with all the cement trucks over to Los Gatos over a mountain road. So the question to me is, hey Jim, are you going to lease an autonomous car next time? I am. Because like Martin, I trust him, right? So let me ask them if they trust themselves, right? So gentlemen, Martin, would you buy an autonomous car next time you buy a car?
I would love to, because that's like really where I would spend money. I'm usually like, I don't need an expensive car, but if someone tells me, okay, you need to pay $10,000 more and then it will be autonomous, I will do it immediately because I can save time. That's the biggest market.
Generation X is spoken.
Yeah.
Okay.
But I would be very careful. Like if they tell me, for instance, okay,
It
today
would have to be Bosch stuff, right?
Yeah, of course.
Okay, all right.
And today in the morning we learned about machine learning, that this can be in a car. But machine learning is something that gives me a feeling, okay, there's some probabilistic stuff going on. But I want someone like him to prove that it's always safe,
Yeah.
And like, then it's a question, They said, okay, AlphaGo is the best machine learning algorithm that can beat people in a Go play, And do I accept that I have only a survival chance of 99.99%, or do I want 100% and then again some percentage that the proof might be wrong that it's 100%?
Yeah. So, well, Ned, instead of your midlife Porsche 911, you're going to buy this car here. Are you ready to buy that car?
Styling may change, but actually, I would put a couple of caveats in it. Yes, as long as it's been crash tested, and by that I mean it didn't pass because it stopped before it crashed. So it needs to be truly crash tested. 1, 2, it needs an override mode, because both from Philippe's standpoint as well as my compulsive standpoint, it's great for commute to do autonomous.
For sure.
I need my fun or override when I drive. So, but I would certainly believe the technology is much closer to being there.
You guys might not believe it, but the big man drives a Boxster. I don't know how he gets in it, right? Yeah. So the next car, is it an autonomous car?
Certainly not. No, I like driving.
What do you think? I'm crazy?
I like driving myself. I'm the biggest risk, so I want to keep it that way.
Okay.
But I will certainly have a self-driving car taking me from my home and driving me to work and park itself or go where else it needs to be. So that's what I want to have. I want to have a service run that does that for me, like an Uber with a self-driver, whatever thing. So coming back to that question earlier on trust. So what we do, and that's along the EDA industry and also in the ISO standard, is you don't have just one technology or one thing you do. You always have several aspects of targeting these questions, and that's in our case coverage. So you don't trust your proof. You have also a coverage measure, a precise coverage measure of what you have proven, and in terms of if there was a bug, would the assertion still go through, or would you find it? And That's very important. That's something that the EDA industry has in the simulation world. We have it also in Formel now. That pattern repeats again. So don't trust just one guy. Have another way of looking at it, and potentially from a different angle to see if this is really the case. And your example with the crash test is the same thing. It's a failover mechanism. Something if it breaks, I'm still safe because there's something else protecting me from the worst. And so I would agree. I would have liked them to be crash tested.
Yes, a few times. So, Philippe, you're driving through the French Alps, right? Every day to work in Grenoble, right? Now, are you going to give up that driving experience to be autonomously driven?
Thanks for stealing my thunder, but yes, I was going to just say the same thing. So my commute to work is 10 minutes, sometimes 15 minutes. So not a big problem to solve. I may be compelled to answer cell phone calls or sometimes urgent emails, but I try to resist that. But the rest of the, other than work days, obviously the weekends, I like to go driving up the Alps, and I want to be fully in control of that, whatever the risk entailed with that may be. So having said that, yes, no, I do see value, joke aside. I do sometimes do longer trips for travel, and I do travel a lot, like all of us, to unknown places, and I wish, I still, rent cars, and but discovering, how to get out of the airport for one, getting to the hotel with 12 hours jet lag, this is not a very nice experience. Yep. I would 100% go for autonomous driving to remove that experience from my life.
Yeah, so what you're saying is that, look, I don't want to use it at home, but sure, the rental yard, they can buy them, right? Hey, I want to do another little experiment. Okay, you guys, same question by show of hands. Next car, would you get an autonomous car, yes or no? Yes with hands. There's some brave souls here, man. Awesome. Well, thanks a lot for listening to us for this hour or so. I want to thank my august panel. Please give them some applause. At least like Martin, I'm going to trust him, man. I'm going to put my own faith, drive my family along playing checkers in the back seat, so looking forward to it. Thanks a lot. We'll see you next DAC.